Hello teacher, hello my friend. Welcome to our presentation. My name is Nhật. Full name is Đặng Quang Nhật and with my team. My team includes Tiên Quang, Nguyễn Quang Quân and Nelson Two Trung Hoa Viết. I will present our project DC to DC Food Converter Design for Solar Electric System. Uh, uh, Supervisor, my teacher Kim Trúc for class 2132. Um, we are excited to share our work. Make um, abstract. Our project decided 12 videos to 20 videos DC to DC boost converter for solar inverters using 20 kilohertz switching and 20 percent duty circle um, simulated and validated with Mudesim and OrCAD. The hardware achieved the required 24 with this output. Um, report content, tab 1, introduction, tab 2, design concept and project development, tab 3, research and analysis. Tab 3 includes 1, circuit design, 2, simulation result, 3, for this calculator part in the part, particle research for constructing and constructing particular circuit by input and output for this 6 output put with modulation 6 7 for this related part 8 the up the operation of the hardware DC to DC converter type to tab 4 for conclusion. And divide the presentation Quang Nhật, Quang Quân and Viết. Tab 1 introduction. Picture 1. This diagram shows a typical solar electric system. A PVT module fit a solar chain controller carrying a battery. The battery powers a DC load directly or DC loads via a DC to AC converters. Our project focused on the highlight DC to DC boost converter, uh, uh, which steps up the battery for this for the inverter or higher for this DC loaders. Tab 3 and tab 2 design concept and project development. This diagram shows a typical solar electric system. Picture 2 shows our sequential development process. Um, uh, designing the boost commuter, simulation of the boost commuter includes using multi-sim and AutoCAD for ALICE and adjustment and constructing the boost converter includes building the hardware. Next. Table 1 preset our case design parameter we use tell VDS input to achieve a 24 place output with a 20 hard disk switching frequency and 50% duty circle the inductor circuit was 2.48 with a maximum for about 4.28 and minimum of 0.58. I mean, for a certain report of 2.5%. Top 3 research analysis one circuit design. Picture 3 show our boost converter circuit. It include tell both voltage DC boost V1 and AT V100 inductor L1 and MOSFET switch M1 ERF 540 controllers by PWM signal diode D1 and 4002 47 for Captrico C1 and tell load PW1 signal operates at 12 kHz with 50% duty circle 10 and 12 this input to the step up to 24 days. That Steven mentioned
Thank you for explaining the design concept. I am Quân. Now I will move on to chapter 3, which focus on simulation, voltage regulation, hardware setup, and testing. Let's start with the simulation result. In Figure 4, you can see the theories waveform of inductor current and voltage in the boost converter. The children is triangle shape. The voltage look like square wedge. In figure 5 and 6, we show the real simulation result from multi-sim. This graph confirms that conductor work in continuous conduction mode, meaning the conductor current never drop to zero. That was this much the conductor stable and efficient. In figure 7, we put both current and voltage waveform together. It shows how switching works. Finally, figure 8 shows output voltage waveform from simulation. It's about 24 points for 35 volts, a bit higher than the target 24 volts, which does a good result. To make sure the input to push converter is stable at 12 volts, we add a voltage regulator. In figure 9, you can see the actual voltage regulator circuit. This is important because the battery output can vary, sometimes reaching up to 13.8 volts. Then in figure 10, the simulated output of the regulator is shown 11.96 volts, which very close to up 12 volts. This shows that the regulator carefully ensure a stable input for boost converter. Now, let's take a look at table 2, which compares theory value with simulation result. Overall, the simulation is very close to calculated value. This confirms that our design is constant and reliable. Let's talk about the Hawkeye contraction. In figure 11, we show the full boost converter circuit. Figure 12 is a photo of a real Hawkeye setup. We built the circuit and tested it using a digital oscilloscope. This proves that our design also works in real life, not just in simulation. In figure 13, we show the input voltage waveform measured from oscilloscope. It's like close to 12.91 volts. So the voltage regulator is working. Then in figure 14, the output voltage is about 58 volts. That's even better than 24 volts, which means the converter is working very well. It's suitable for devices such as DC fans or inverter. Overall, in short, boost converter works well. It's a good option for solo electric system. That's the end of my post. Now, let's continue with the next section of presentation. I would like to invite my teammates to come up and present the rest of our project.
Hello, Miss Trúc. My name is Trương Bảo Biết, and thank you, Miss Quân and Miss Nhật, for their presentation. To continue the presentation, I will discuss the rest of the article with everyone. First of all, let's discuss the pulse width modulation, as you know, PWM. PWM is a technique used to control the amount of the power delivers to a low by changing the duty cycle of the signal. In the context of the boost converter, PWM is essential for controlling the circuit of the MOSFET, which directly affects the output voltages. And in this process, PWM signal is generated using TDA 2004 IC, specifically pins 10 and pin 8 of the IC output the PWM signal. You can see in the figure 16 the PWM from pin 10 and pin 8 from the oscilloscope. And table 4 shows the comparison between calculations, simulation, and practical output values. Interestingly, while the design and simulation assume a duty cycle of 50%, the measurement from the hardware show the duty cycle of 33%. This difference could be due to several factors such as component tolerance or measurement. Despite this difference, the output voltage still met the 24 voltages. Next, let's move to voltage regulator part. Since the input to the boost converter comes from a battery that can output 14 voltages, a voltage regulator is used to ensure a stable 12 voltage input. This is crucial because the boost converter is designed for 12 voltage input, and any variations could be affect its performance. The output waveform from the IC is stable and is close to 12 voltages close to target. Now, let's talk about the operation of the hardware. The DC to DC boost converter is designed to operation standalone, providing a regulated 24 voltages output from a 12 voltage input. It can deliver a current ranging from 0 to 2.5 ampere, making it suitable for driving loads such as PC fans, DC ceiling fans, and so on. Finally, in conclusion, the project successfully developed a DC to DC boost converter, thus convert 12 voltages to 24 voltages as evidenced by both simulation and hardware results. The output voltages from the hardware were measurement approximately 24 voltages, very close to target. Although there are some difference in the duty cycle, the overall performance met the requirements. And this is the references. Thank you for your listening.